This is the final part of a series on the AdaBoost. In the last 3 videos, we looked at binary and multi-class classification. In this video, we will look at AdaBoost's regression algorithm. Let's first analyze AdaBoost's regression algorithm and then implement it in code. Finally, let's try using scikit-learn's AdaBoostRegressor library and compare the results with those of our previous code. In 1997, Drucker proposed the AdaBoost Regression algorithm. In the paper below, by modifying Freund's 1995 classification algorithm. In this paper, the regression algorithm was introduced through these procedures. Let's look at the procedures presented in the paper one by one. In step 1, we initialize the sampling weights to 1 over n, where n is the number of data points, and the sampling is performed with replacement according to the weights. Then, a training set is created from the sampled data. This is a subset, and repeat the process below. In step 2, we create a regression model and train the model using the subset is HT. In step 3, the entire training data is input to this model to predict the target value Y. Predict all n data points. The step 4 calculates the loss. The loss is calculated as the difference between the predicted and actual values for each data point, and we make the loss range between 0 and 1. There are 3 types of losses as follows. The first one is linear loss, where D is the maximum value of loss. We then normalize the loss by dividing it by D to make it a value between 0 and 1. The second one is square loss. We also normalize this loss by dividing it by D squared. And the third one is the exponential loss. These losses correspond to the misclassified error rate used in the classification algorithm. The step 5 calculates the average loss over the entire data points. Calculate the weighted average by multiplying the loss of each data point by its sampling weight and adding them all together. In step 6, we use the average loss to calculate beta using this formula. The beta is proportional to the average loss. The smaller the beta, the smaller the average loss, and the more reliable the estimates from this model. The step 7 calculates new sampling weights to be used in the next iteration round. As average loss increases, beta also increases exponentially. And as the loss of each data point increases, this value increases like this. If the loss is small, this value will also be small. The smaller the loss, the smaller the sampling weight, and the less data is sampled. Conversely, the larger the loss, the larger this value will be. Data points with less error and better predictions are sampled less frequently in the next round. On the other hand, data points with more error and worse predictions are sampled more frequently. This is equivalent to updating the weights in the classification algorithm. This is the training process. The step 8 is the prediction process. Use the trained models to predict test data and synthesize the results. The final prediction result is determined by this formula. This is the weighted median of the prediction values from the models. Here, log 1 over beta serves as the alpha we looked at in the classification algorithm. Since beta is proportional to loss, this value is inversely proportional to loss. This is the weight to apply to each model. Therefore, the weight of the model with a large loss decreases. This is also the case with the classification algorithm. The formula for calculating the weighted median is discussed in detail on the next page. In step 8, the weighted median was used for the final prediction. However, we can also simply use a weighted average. We'll try both methods here. On this page, the weight applied to each model is denoted by W. This is not the sampling weight applied to each data point. It plays the same role as alpha used in the classification algorithm. And we normalize this. Let's use a weighted average as the first method. There are T models trained in the training stage. When the test data is input into the models, each model outputs the target value like this. Multiplying these outputs by the model weights and adding them all together results in a weighted average. And this is the final estimate, HF. It can be simply implemented with the following code. Here, ypred is actually a two-dimensional structure like this. The first row is the prediction results of the first test data point, and the second is the prediction results of the second test data point. It's multiplied by the weight vector like this. The second method is to use the weighted median as shown in the paper. The formula presented in the paper is as follows. Log 1 over beta is the weight, so we will write it as W. When the predicted Y is sorted in ascending order, the Y at the first position where the sum of the lower W is greater than half of the total sum of W becomes the final prediction. This is the weighted median. Let me give you an example. When T is 50, there are a total of 50 Y values predicted by each of the 50 models. Y0 is the value predicted by the first model. And sort these values in ascending order. For example, let's say the result is like this. The smallest is the Y3 at the position 3, and the next smallest is the Y0 at the position 0. These are the indices for predicted Y values. And the weight W corresponding to each Y value will be as follows. Then accumulate this W. The sum of these two values is A1, and the sum of these three values is A2. The last value, A49, is the sum of all W. Next, find the position where the value of A is half of A49. Let's say the position is here. This is the location of the weighted median. For example, let's say it is 23. Then Y in the 23rd position is at this position. Then the Y value of this location is Y34. So the final prediction is the Y34 value. If you write this process in code, it looks like this. Ipred is the sorting of Ypred in ascending order. And WAC is the accumulation of the weights. And if we find the first position, where the WAC is greater than 0.5 times the total weight, that's the final weighted median position. This is the method of finding the final predicted value using the weighted median. Now let's implement this algorithm in code. We will implement it using Decision Tree Regressor as a base learner. And we will also implement this using the AdaBoostRegressor and compare the two results. The data we will use is like this. Data is a mixture of sinusoids and noise. The number of features is 1, and the Y is the target value. We generated 500 of these data points. N is the number of data points, and R is the index of all data points like this. And T is the maximum number of models set to 100. In the first step, the initial sampling weights are set uniformly to 1 over n. And with 100 iterations, up to 100 models are created. Sample n data points from the entire dataset according to the sampling weights. This is a subset of the sampled data. Then we create a base learner model. A decision tree is used as the base learner, and the tree depth is set to 5. We then fit this model to the subset. Now let's calculate the loss. Input the entire data into this model to predict the target y value. The error is calculated as the difference between the predicted value and the actual value. This part is the error. We then use this formula to calculate the squared loss for each data point. Next, we calculate the average loss using this formula. And repeat this process while the average loss is less than 0.5. If the average loss is greater than 0.5, then stop iterations. Next, we use this formula to calculate the beta. We then use this beta to calculate the sampling weights for the next iteration round. And the weights are normalized. In the next round, the data is sampled using the updated sampling weights. Repeating this is the training process, creating models and calculating betas. Next, we will generate test data, predict target values for the test data, and visually check the results. Now let's look at the prediction process. We will generate 50 pieces of test data. 50 test data points are generated sequentially, ranging from 0 to 1. In the figure below, the test data will look like this. We want to predict the y value of each test data point. And we use this formula to calculate the weight for each model. The trained models are then used to predict target values on the test data. This is the y-pred. The y-pred contains the prediction results of each model. Now we need to put these results together to create the final prediction. We'll try both methods here. The first method is simply to calculate the weighted average. Normalize log beta and use it as the weight of the model. And calculate the weighted average of y-pred. This is the final prediction by the first method. Then visualize the training and test data to see the results. The result is like this. The blue dots are training data points, and the red chart is the weighted average prediction of the test data. You can see that the y value of each test data point forms a sine curve. Next, we will use the weighted median as shown in the paper. As described earlier, we sort the predicted y in ascending order and accumulate the weights, then find the location of the weighted median. The predicted y at that location then becomes the final prediction. Visually check this result as well. It looks like this. You can see that the results are similar to the results on the left. This time, we'll use scikit-learn's AdaBoostRegressor. We use decision tree regressor as the base learner and set the tree depth to 5 as before. And then we create the model using AdaBoostRegressor. The base learner is decision tree and the number of models is 100. We use squared loss. Then, fit the model to the training data and predict the target value of the test data. We also check the result visually through the Y values of the training and test data. You can see that the result is the same as the result on the left. Scikit-learn also uses the weighted median, so the result on the left is the same. AdaBoostRegressor makes this very easy to implement. Let's run this code. This is the result. So far, we have looked at the AdaBoost algorithm through a total of 4 videos. We looked at binary classification, multi-class classification, and regression.